Let's practice finding right-hand Riemann sums. So the directions here say to calculate the right Riemann sum for 400, and in rectangles for f of x equals 5 minus 1/2 x squared on the interval from 0 to 2. Okay, so you already know, right, that Riemann sums give us a way to estimate the area under a curve by taking that area and dividing it into rectangles and then summing the area of each rectangle. So here I've written the formula for the right Riemann sum, right? So I have the area equals the sum from k equals 1 to n of f of a plus k delta x. Okay, that gives me the height of each rectangle, and then times delta x, and delta x is the width of each rectangle. So I'm finding the area of each rectangle by taking its height times its width and then summing these up. And this formula gives me a concise way to do that. Okay, so let's start by doing this for 4 rectangles. And I've illustrated this case here. Okay, so here I have 4 rectangles, right? I'm going from a equals 0 to b equals 2, 4 rectangles. And it's a right Riemann sum because the height of the rectangle is given by the right endpoint, okay, which is at the function height. Okay, so let's go ahead and plug in. So we want to use this formula. So first let's think about the relevant pieces that we need. So 4 rectangles tells me that n equals 4. Okay, I need to know what n is, right? That's part of my formula. So if I just glance through my formula, what else? Well, I have f. That just represents the function. So in our case, f of x was 5 minus 1/2 x squared. Okay, then I have f of a. A is just represents the left endpoint. So in my case, a equals 0. Plus k delta x. Now k is just the index that I'm summing over, but let's calculate delta x. Delta x is the width of each rectangle, and it's b minus a over n, which in my case is 2 minus 0 over 4. Okay, so 2 over 4, which is 1/2. Okay, so my delta x is 1/2. Okay, so now that we have all the pieces, let's go ahead and plug these into the formula and get our Riemann sum formula. So area equals the sum from k equals 1 to n, but n equals 4 for us, f of a, which is 0, plus k times delta x, and delta x was 1/2, so that's k times 1/2, or I can write that as 1/2 k, times delta x again, which was 1/2. Still have a lot of work to do, but just writing that down is a very important step. Okay. So one thing I can do just to make this a little nicer, this 1/2 is a constant multiple, right? So I can go ahead and pull that out front, this 1/2 right here. So if I pull that out front, I have 1/2 times the sum from k equals 1 to 4 of f of 0 plus 1/2 k. Okay, well, what is that? F of 0 plus 1/2 k. What that's telling us to do is take this expression, 0 plus 1/2 k, and plug it into f of x. Okay, so if I do that, so my f of x is 5 minus 1/2 x squared, 5 minus 1/2, and I'm taking this expression, 0 plus 1/2 k, and plugging it in. So now I have 1/2 times 0 plus 1/2 k quantity squared. And that's all inside my summation. Okay. So now if I clean that up a little bit, we've got 5 minus 1/2 times 1/2 k quantity squared. Okay, and we keep going here. 5 minus 1/2. If I actually square this, okay, that's going to give me k squared over 4. Now, let me just say something really quick. This was kind of nice because a was 0, right? But let's say a had been 1, for example. Then I'd be squaring 1 plus 1/2 k, right? My expression in here would be 1 plus 1/2 k. To square that, you'd have to FOIL it out. Okay, so just be careful and FOIL whenever you need to. But here it was nice we didn't have to FOIL. So now we have this, and I can maybe do one more step to clean that up, and write this as 5 minus k squared over 8. Okay, so I'm looking to get a number here. I'm looking to get a numeric value. So now I have this sum of 5 minus k squared over 8. But remember, we learned all those nice summation formulas, so I can actually use those to find a numeric value for this sum. So first, let's split it up. Okay, so I have 1/2 out front, but I can split up this sum into two pieces. The sum of 5 minus, and I'm going to pull this constant out front, 1/8 times the sum of k squared. And now I just use my summation formulas for constant and for k squared. Okay, and let me just paste those out to the side to remind us of what those are. Okay. Formulas out here. So let's use those. So I still keep my 1/2 out front. So here I have the sum of a constant. So I'm told over here, right, that the sum of a constant is c times n. Well, my n is 4, so this is 5 times 4, minus 1/8 times k squared. Now k squared is given by this expression here, so a little messy. My n is 4, so if I plug that in, I'm going to get 4 times 4 plus 1 is just 5, times 2 times 4 plus 1, which is 9, all over 6. Okay, and then I just need to work that out. Okay, so let's see. 5 times 4 is going to give us 20. If you work this out, you should get 3.75. And if you work that out, your final answer should be 8.125. Okay, so using 4 rectangles, this is the estimate we get for the area under the curve. Now, if we just glance back up at the picture, we see that that's an underestimate, right? Okay. But anyway, this is what we get for 4 rectangles. So next we want to do this for 400 rectangles. Okay, so let's try that next. Okay, so here again is our right Riemann sum formula, our function, and the interval we're interested in. So let's again start by writing down the pieces of information that we're going to need to plug into the Riemann sum formula. Okay, so if we're doing 400 rectangles, then n is 400, and a is still the left-hand endpoint, so a is the same, it's still 0. And the other important thing I need is delta x. Okay, so remember delta x is b minus a over n. So here that's 2 minus 0 over 400 this time. So that's 2 over 400, or 1 over 200. Okay, and then we're going to take all this information and plug it into the Riemann sum formula. So if I do that, it's going to look like this. The sum from k equals 1 to n, but my n is 400. Okay, then I have this f of a plus k delta x, that whole expression. Remember, that just represents the height of each rectangle using right-hand endpoints. So if I plug in my information, that's 0 plus k times delta x, so that's 1 over 200k. And then times delta x, and now this is the width of each rectangle, so times 1 over 200. Okay, now from here this is going to be quite similar to what we did before. I'm going to pull this 1 over 200 out front. So I have f of k over 200. And then I'm going to actually stick my function in there, or rather, the better way to put it probably is stick k over 200 into my function. And if I do that, it's going to look like 5 minus 1/2 times k over 200 quantity squared, right? So I'm just taking my function and evaluating it at k over 200, plugging that in for x. Okay, so let's do a little cleanup here and get this as nice as possible so we can use our summation formulas. Okay, well, this is k squared over 40,000. if you actually square it. And then that, in turn, is going to give me 5 minus k squared over 80,000. Okay, now remember last time what we did is we split this up, so let's do that again. So I want to keep the 1 over 200 out in front of everything, but I'm going to split up this sum into two pieces. So k equals 1 to 400 of 5, the sum of 5, minus, I can pull this constant out front, so 1 over 80,000 from k equals 1 to 400 of k squared. Okay, and then once again, I want to use my summation formulas here to evaluate these sums and get a numeric answer. Okay, so here are those again, and let's use those. So I have the sum of 5. Now that's a constant, so it's going to equal that constant times n, and n is 400. So that's going to be 5 times 400 minus 1 over 80,000 times, okay, k squared with n equals 400. So n is 400 times n plus 1 should be 401 times 2n plus 1 should be 801, and that's all over 6. And from here, it's just plug and chug in your calculator. So let's see. Inside these brackets, I should get 2,000 minus 267.6675. And if you just finish that out, you should get approximately 8.66. Okay, so this is my estimate if I'm using 400 rectangles. And because I'm using more rectangles, it should be a better estimate than for when I used 4 rectangles. Now let's see if that makes sense. Okay, it's always a good idea to check and make sure your answer makes sense. So we said, okay, that when we were using 4 rectangles, that it was an underestimate. And that's because we're using right-hand endpoints, right? Because of the shape of this function, the right-hand endpoint is going to give us an underestimate. So then we expect that when we use more rectangles, we get a better estimate. It should be a higher number, right? Because it was an underestimate, but it's getting better, so it should be larger. And that's what happened, right? We got 8.125, and then we got 8.66. Okay, so that's less of an underestimate, closer to the exact area. Okay, so the last thing we want to do is we want to find a generic formula for just n rectangles in general. So I found values or areas for specific numbers of rectangles, but can I just come up with an area formula for n rectangles? And I could plug any n into it and get the estimate for that many rectangles. Okay, so that's what we're going to do here. And it's going to be a very similar process. So once again, we're going to use our right-hand Riemann sum formula. So remember that looked like this. F of a plus k delta x, that's the height of each rectangle, times the width of each rectangle, delta x. And once again, our function was 5 minus 1/2 x squared on the interval from 0 to 2. Okay. So one more time, let's figure out our pieces. So n is just n, right? We're doing this for an n in general. But a is still 0. The left-hand endpoint is still 0. What about delta x? Well, delta x is b minus a over n, which is going to be 2 over n, and it's just going to be in terms of n. Okay. So let's take this and plug it into our formula. So area equals the sum from k equals 1 to n, f of 0 plus k times delta x, and delta x is 2 over n. So I can write that as 2k over n times 2 over n. Now 2 over n is actually a constant. That might seem a little weird, but look at what we're summing over. We're summing over k. So with respect to this summation, n is a constant, so I can pull that out front. and it's going to look like this. F of 2k over n. And now, like I've done in all the other ones, I'm going to take 2k over n and plug it into my function. Okay, so if I do that, then I have 5 minus 1/2 times 2k over n quantity squared, and all that's inside the summation. Okay, so let's work that out. 5 minus 1/2, if I square that, I get 4k squared over n squared. Okay, and then I can simplify that a little bit. 5 minus, so the 4 and the 2 are going to cancel, and I'm going to get 2k squared over n squared. Okay. Now, once again, we're going to proceed like we did before and split up this summation. So 2 over n is out front of everything, but then I can split this up into the sum of 5 minus, now the constants here are 2 over n squared, so I pull them out, and then I have the sum of k squared. And now I use my formulas again. So 2 over n. The sum of a constant is that constant times n. So that's just 5n. Minus 2 over n squared times the sum of k squared, and we have a formula for that. It's n plus 1 times 2n plus 1 all over 6. So you can see we're doing the exact same thing we did before. We're just leaving things in terms of n instead of plugging in a specific value. But besides that, exactly the same process. I can simplify this a little bit, right? I have this n, these are being multiplied, right? So I have this n up here and n squared, and then a 2 and a 6. Okay, so this becomes n plus 1, 2n plus 1 over 3n. And I'm just going to go ahead and just distribute that 2 over n to the terms inside the brackets. So that would give me 10 minus, let's see, 2n plus 1, 2n plus 1 over 3n squared. Now you can check this, right? So this gives us a generic formula for the area approximation, or the right-hand Riemann sum, for any n that we want. So if you took 4 and plugged it in here, you should get what we previously got for 4 rectangles. If you take 400 and plug it in, you should get what we previously got for 400 rectangles. So you can check that if you want. And the larger the value of n you plug in, the better the approximation is going to be here.